Welcome to this problem-solving session. Today, we will tackle LeetCode problem number 468, validate IP address. This problem challenges us to determine whether a given string represents a valid IPv4 address, IPv6 address, or neither. It's a fantastic exercise in string parsing and edge case handling, so let's dive in. In this problem, we are tasked with validating whether a given string, query IP, represents a valid IP address. The function should return IPv4 if the input is a valid IPv4 address, IPv6 if it is a valid IPv6 address, or neither if it does not satisfy the format of either type. Now, let's break down the requirements for both types of IP addresses. For IPv4, the address consists of 4 decimal numbers separated by dots, where each number must be between 0 and 255. Importantly, these numbers cannot have leading zeros, so something like 192.168.01.1 is invalid. Additionally, each number can have at most 3 characters. On the other hand, an IPv6 address consists of 8 groups of hexadecimal numbers separated by colons. Each group can have between 1 and 4 digits, and these digits can be in the range of 0 to 9 or AF, whether lowercase or uppercase. Leading zeros are allowed in IPv6 groups, but the address cannot have extra colons or an incorrect number of groups. If the given input doesn't meet these criteria for either IPv4 or IPv6, the output should be neither. To better understand these rules, let's look at some examples. For the input query IP equals 172.16.254.1, the output is IPv4. This is because the string meets all the criteria for a valid IPv4 address. It has 4 groups separated by dots, and each group 172, 16, 254, and 1 is a valid number within the range of 0 to 255. Additionally, none of the groups have leading zeros, so the address is valid. Now, for the input query IP equals 2001:0 we get the output IPv6. This is because the address 2001:0db8:0:0:8A2E037:0:7334 satisfies the format for an IPv6 address. It consists of 8 groups separated by colons, and each group contains valid hexadecimal digits. Additionally, there are no extra colons, and the address has exactly 8 groups. Next, let's consider the input query IP equals 256.256.256.256. The output for this input is neither. Here, the address 256.256.256.256 fails to meet the criteria for a valid IPv4 address because each group in an IPv4 address must be a number between 0 and 255. In this case, all the groups exceed this range, making the address invalid. Another example is query IP equals 1E1.4.5.6, which also outputs neither. This is because the group 1 times 10 to the power of 1 contains invalid characters. Letters are not allowed in an IPv4 address. These examples highlight some common pitfalls to watch out for when validating IP addresses. Finally, there are additional edge cases and constraints to consider. For instance, an IPv4 address may have invalid formatting due to extra separators or missing groups, such as 192.1.1 or 192.1.1.1, which are both invalid. Similarly, an IPv6 address must have exactly 8 groups, so addresses with fewer or more groups, or those containing invalid characters like 2001 DB8 85A3 XYZ, are not valid. The string query IP is guaranteed to consist only of printable ASCII characters, and its length will be between 1 and 200. By carefully checking these cases, we can ensure the function correctly identifies valid and invalid IP addresses. To address the challenge of validating whether a string represents a valid IPv4, IPv6, or neither, we need a reliable and robust string parsing solution. Let's first consider the brute force approach. This method involves manually parsing the input string character by character to validate whether it adheres to the rules for IPv4 or IPv6. While this approach is straightforward and directly tackles the problem, it comes with significant downsides. It requires extensive string manipulation and splitting, making it cumbersome to implement and debug. Additionally, such a method involves a lot of branching logic, which can negatively impact performance, especially when handling edge cases or malformed inputs. Another approach that is often considered is using regular expressions, or regex. Regex allows us to precisely define the format of IPv4 and IPv6 addresses, making it a popular choice. For instance, we can use regex to verify that an IPv4 address consists of 4 separated integers between 0 and 255, or that an IPv6 address has 8 separated hexadecimal groups. However, there are trade-offs here as well. While regex is concise and clear, it can be computationally expensive due to the overhead of compiling and executing complex patterns. Moreover, debugging regex can be particularly challenging when dealing with intricate inputs or subtle errors in the pattern definition. Now, let's examine the optimized parsing and validation approach, which is the strategy we've chosen. This method strikes a balance between simplicity, performance, and maintainability. Instead of relying on brute force or regex, we split the input string based on its delimiters, periods for IPv4 and colons for IPv6, and validate each segment iteratively. For IPv4 addresses, this involves ensuring there are exactly 4 segments, each representing an integer between 0 and 255, with no leading zeros. For IPv6 addresses, we check for exactly 8 segments, each containing a valid hexadecimal value and conforming to the length restriction of 1 to 4 characters. This approach explicitly handles edge cases, such as empty segments, invalid characters, or improper formatting, making it both robust and reliable. The key intuition behind this strategy is that IPv4 and IPv6 addresses follow strict structural rules that can be easily validated using simple string operations. By leveraging built-in functions for string manipulation, we can create a solution that is efficient, easy to understand, and resilient to errors. This approach not only avoids the performance penalties associated with regex but also provides a cleaner and more readable implementation compared to brute force methods. Finally, let's consider the trade-offs between the different approaches. Using regex offers a concise solution, but it can be harder to maintain and debug, especially as input complexity increases. The brute force approach, while simple in concept, is inefficient and prone to errors due to its reliance on extensive manual checks. In contrast, the chosen approach of optimized parsing and validation is slightly more verbose but shines in clarity, efficiency, and maintainability. When analyzing the complexity, this method demonstrates strong performance characteristics. The time complexity is O(n), where n is the length of the input string. This is because we process each character exactly once during the splitting and validation steps. The space complexity is O(1), as the solution uses a constant amount of additional memory beyond the input string itself. By combining these advantages, this approach ensures that we handle all edge cases and inputs effectively, making it the most appropriate and practical solution for validating IP addresses. To determine whether a given string is a valid IPv4 or IPv6 address, or neither, we need a systematic approach that accounts for all potential edge cases. The first step is input validation. This step ensures that the input string is neither empty nor null, as these are immediately considered invalid. If the input string is empty, we simply return neither without further checks. Next, we identify the format of the address based on its structure. If the string contains dots, it suggests an IPv4 format, while colons indicate a potential IPv6 format. If the string contains neither, it's clear that it cannot be a valid IP address, and we return neither as the result. This format determination is crucial because the subsequent validation rules depend entirely on whether the address is IPv4 or IPv6. Once we've identified that the address might be IPv4, we proceed with its specific validation rules. IPv4 addresses are made up of 4 separated segments, so the first step is to split the string by dots. If the resulting list does not contain exactly 4 segments, the address is invalid, and we return neither. For each segment, we ensure it only contains numeric characters, no letters, symbols, or empty segments are allowed. Additionally, the numeric value of each segment must fall within the range of 0 to 255. An important edge case here is leading zeros, such as O(1), which are not allowed even though they are technically numeric. If all of these conditions are met for every segment, we can confidently return IPv4 as the result. Otherwise, the address is invalid, and we move on to other checks. If the address appears to follow an IPv6 format, we apply a different set of rules for validation. An IPv6 address consists of 8 colon-separated segments, so we begin by splitting the input string using colons. If the resulting list doesn't contain exactly 8 segments, the address is invalid, and we return neither. For each segment, we verify that it represents a valid hexadecimal value. This means it can include digits 0 to 9 and letters AF or AF. Additionally, the length of each segment must be between 1 and 4 characters. Any segment that fails these checks disqualifies the address from being a valid IPv6 address. If all segments satisfy these requirements, we return IPv6. If neither the IPv4 nor the IPv6 checks are successful, the address is determined to be invalid, and we return neither as the final result. When solving this problem, it's essential to consider several key insights to ensure robust validation. For example, edge cases such as empty strings, extra delimiters like double dots or colons, and improperly formatted segments must all be handled carefully. IPv4 segments with leading zeros, such as 01, are explicitly invalid, while IPv6 segments must strictly adhere to being valid hexadecimal strings no longer than 4 characters. From an efficiency perspective, the operations involved, string splitting and segment validation, are linear in complexity relative to the length of the string, making this approach computationally efficient. Additionally, proper error handling is crucial. If the input contains invalid characters or doesn't conform to expected formats, it's important to return neither immediately to avoid unnecessary computation. The use of strings and lists as data structures allows for straightforward manipulation of the input and its segments, simplifying the overall validation process. The data flow for this algorithm can be visualized as a series of logical steps. First, the input string, such as 192.168.0.1, is received and checked to ensure it is not empty. Next, the format of the address is identified based on the presence of dots or colons, which indicate potential IPv4 or IPv6 formats, respectively. Following this, the string is split into segments, and each segment is validated according to the rules of its respective format. For IPv4, the segments must be numeric and fall within a specific range. For IPv6, the segments must be valid hexadecimal strings of appropriate length. Finally, based on the results of these validations, the algorithm outputs IPv4, IPv6, or neither, providing a clear determination of the input's validity as an IP address. Here, we start by defining a class called solution and a method within it named validIPAddress, which takes a single input, query IP. To validate if the input is an IPv4 address, we define a helper function called isIPv4. In this function, we first split the input string using the period dot as the delimiter. If the resulting list doesn't contain exactly 4 parts, we immediately return false since an IPv4 address must have 4 octets. Then, we iterate through each part to check specific conditions. Each part must be a digit, and its value should fall within the range of 0 to 255. We also ensure that parts with leading zeros, like 01 foot, are flagged as invalid. If any of these conditions fail, we return false. Otherwise, if all parts satisfy the criteria, we return true. Next, we define another helper function, isIPv6, to validate IPv6 addresses. Here, we split the input string using the colon as the delimiter. An IPv6 address must have exactly 8 parts, so if the number of parts is not 8, we return false. We then check additional conditions for each part. The length must be between 1 and 4 characters, and the part must represent a valid hexadecimal number. To ensure this, we attempt to convert it to an integer using base 16. If it fails or the value is outside the range of 0 to 0xFFFF, we return false. If all parts pass these checks, we return true. Now, we use the helper functions to determine the type of IP address. First, we check if the input contains 3 dots, indicating it could be an IPv4 address. If this condition is true and the isIPv4 function confirms its validity, we return IPv4. Otherwise, we check if the input contains 7 colons, suggesting it could be an IPv6 address. If so, and the isIPv6 function validates the address, we return IPv6. If neither condition is met, meaning the input doesn't conform to the format of an IPv4 or IPv6 address, we return neither. This structure ensures that we thoroughly validate the input against both IP address formats and return the appropriate result. Here, we begin by defining a method called valid IP address, which takes a string query IP as input. The goal of this method is to determine if the input string represents a valid IPv4 address, a valid IPv6 address, or neither. First, we check if the query IP contains exactly 3 dots by counting occurrences of the dot character. If it does, we call the helper method as IPv4 to validate the structure as an IPv4 address. Similarly, if the string contains exactly 7 colons, we call the isIPv6 method to check if it conforms to the IPv6 format. If neither condition is met, we return neither to indicate that the input string is not a valid IP address. The isIPv4 method begins by splitting the input string into parts based on the dot delimiter. After splitting, we verify that there are exactly 4 parts to ensure it matches the IPv4 structure. If not, the method returns false immediately. Next, we iterate through each part to validate its specific criteria, such as ensuring it's non-empty and its length does not exceed 3 characters. Additionally, we check each character in the part to confirm that it is a digit. Once we verify that all characters in a part are digits, we parse the part into an integer. We then check if the resulting number is within the valid range for IPv4, which is 0 to 255. If the number is outside this range, or if the part contains leading zeros while having more than 1 character, we return false. If all parts pass these checks, the isIPv4 method returns true, confirming that the input string is a valid IPv4 address. Moving on to the isIPv6 method, it begins by splitting the input string into parts using the colon delimiter. For IPv6, we expect exactly 8 parts, so if the length of the resulting array is not 8, the method immediately returns false. Each part is then validated to ensure it is non-empty and does not exceed 4 characters in length. We also check that all characters in the part are either digits, lowercase letters from A to F, or uppercase letters from A to F, as these are the valid hexadecimal characters allowed in IPv6. If any part fails these conditions, we return false. If all parts meet the criteria, the method returns true, confirming the input as a valid IPv6 address. Here, we start by addressing the input query IP equals 192.168.1.1, which is to be validated as an IP address. The first step is to check if the input contains exactly 3 dots, indicating a potential IPv4 address. Since this condition is met, the isIPv4 helper function is invoked. Inside isIPv4, the string is split at the dots, resulting in the parts 192, 168, 1, 1. The function ensures that there are exactly 4 parts, which is true in this case. It then proceeds to validate each part. The first part, 192, is checked to ensure it is numeric, within the range of 0 to 255, and does not have leading zeros, all of which are satisfied. Similarly, 168, 1, and the final one also meet all these criteria. Since every part passes validation, isIPv4 returns true. Consequently, the main function identifies the input as a valid IPv4 address and returns the result, IPv4. Now, we consider the input query IP equals 2001:0DB8:0000000000:8A2E0370:7334, which is checked to determine if it is an IPv6 address. The code first verifies that the string contains exactly 7 colons, a hallmark of the IPv6 format. As this condition is satisfied, the isIPv6 helper function is called. Inside isIPv6, the string is split at the colons to obtain the parts 2001:0DB8:85A3:0000:0000, 8A2E:0370:7334. The function ensures there are exactly 8 parts, which is true here. Each part is then validated to confirm it is between 1 and 4 characters long and consists of valid hexadecimal digits. For example, 2001 and 0DB8 are checked and pass these requirements. Similarly, the remaining parts, including 85A3:0000 and 7334, all meet the criteria. Since all parts are valid, isIPv6 returns true. The main function then concludes that the input is a valid IPv6 address and returns the result, IPv6. In this example, we examine the input query IP equals 256.256.256.256, which does not conform to either the IPv4 or IPv6 format. The function first checks for 3 dots to identify a potential IPv4 address. Since this condition is met, the isIPv4 helper function is called. Inside isIPv4, the input is split at the dots, producing the parts 256, 256, 256, 256. The function verifies that there are exactly 4 parts, which is true. It then checks each part for validity. The first part, 256, is numeric, but it exceeds the allowed range of 0 to 255, making it invalid. Since one part fails the check, isIPv4 immediately returns false. Returning to the main function, it then checks for 7 colons to determine if the input could be an IPv6 address, but this condition is not met. As neither isIPv4 nor isIPv6 validates the input, the function concludes that it is neither a valid IPv4 nor IPv6 address and returns the result, neither. The time complexity of the solution is determined by the operations involved in validating the input string as either an IPv4 or IPv6 address. First, counting the delimiters in the input string involves traversing the string to count occurrences of dot and colon. This traversal has a time complexity of O, n, where n is the length of the input string. For IPv4 validation, the string is split into parts using split, but which takes O, n, time, and since IPv4 addresses have at most 4 parts, any operations on these parts, like checking if they are numeric or within a valid range, are constant or linear with respect to the length of each part. This results in an overall complexity of O, k, for the IPv4 validation, where k is the average length of the parts. These steps lay the foundation for understanding how the solution processes an IPv4 address efficiently. For IPv6 validation, the string is split into parts using split, which also takes O, n, time. IPv6 addresses are divided into at most 8 parts. Validations such as checking the length of each part, ensuring it is within bounds, and parsing it as a hexadecimal number each contribute to the complexity. Parsing a hexadecimal string involves processing each character, which takes O, k, time for a part of length k. With 8 parts, this results in a total time complexity of O, k, for IPv6 validation. Combining this with the delimiter counting step, IPv6 validation has a total complexity of O, n plus k. Since the solution performs these checks sequentially and exits early when a valid address type is identified, the overall time complexity of the solution remains O, n plus k, where n is the string length and k is the average part length. The space complexity of the solution primarily comes from storing the parts of the input string after splitting it. For IPv4 validation, splitting the string into parts using split, creates an array of up to 4 parts, with each part requiring O, k, space, where k is the average length of a part. This results in an overall space complexity of O, k, for IPv4. Similarly, for IPv6 validation, the split, operation creates an array of up to 8 parts, and with each part also requiring O, k, space, the space complexity here is O, k, as well. Temporary variables used during validation, such as the current part or its parsed integer value, use only O1, space, which is negligible. No additional data structures or memory-intensive operations contribute to the space complexity, keeping it minimal and focused on the split arrays. The overall space complexity of the solution is dominated by the arrays created during the split operations. For IPv4, this complexity is O, k, as the split operation handles at most 4 parts. For IPv6, the complexity is similarly O, k, since the split operation handles at most 8 parts. Since these checks are performed one after the other, the overall space complexity remains O, k, where k is the average length of one part of the input string. A naive or brute force approach, such as manually parsing the string character by character, might use additional memory for intermediate steps or custom logic, which could increase the space usage. By leveraging Python's built-in functions like split, the current solution avoids such overhead and remains efficient in both time and space. This solution is highly efficient for typical inputs, as the number of parts in IPv4 and IPv6 addresses is fixed, 4 for IPv4 and 8 for IPv6. This ensures that the validation for each part runs in constant time relative to the number of parts. The linear time complexity with respect to the input string length, O, n, makes the solution optimal for this type of problem. The proof of the time complexity lies in the operations that dominate the runtime, delimiter counting and the split operation, both of which are O(n). The validation logic, constrained to a fixed number of parts, adds O(k), where k is the average part length. Together, these steps confirm that the overall complexity of the solution is O(n plus k), balancing efficiency and simplicity. In the best case, the solution quickly identifies an invalid input based on delimiter count. For example, an IPv4 address with fewer than 3 dots or an IPv6 address with fewer than 7 colons is immediately deemed invalid, resulting in a runtime of O(n) for counting delimiters. In the average case, the input requires full validation, including checking all parts for either IPv4 or IPv6, leading to a time complexity of O(n plus k). The worst-case scenario occurs when the input passes delimiter checks but fails validation at the last part, requiring both IPv4 and IPv6 checks to complete. Here, the time complexity also remains O(n plus k). Across all scenarios, the space complexity is consistently O(k), as the solution's memory usage depends only on the parts generated during the split operations. When validating IP addresses, there are some common mistakes to watch out for. One is not handling IPv4 addresses with leading zeros. For example, 01.01.01.01 might seem valid at first glance, but it's actually invalid because IPv4 segments cannot have leading zeros. IPv4 segments must be plain decimal numbers between 0 and 255, and leading zeros indicate an incorrect format. Another mistake is failing to validate the range of IPv4 segments. Consider 256.100.100.100. This is invalid because each segment must stay within the range of 0 to 255, inclusive. Lastly, for IPv6, edge cases like mixed-case hexadecimal or omitted segments are sometimes overlooked. For example, 2001 DB8:85A3 8A2E0370:7334 is valid because IPv6 allows both uppercase and lowercase hexadecimal letters. Similarly, the double colon, smiley face is a shorthand for omitted zeros, which is valid in IPv6. Missing these details can lead to incorrect results, so thorough validation is essential. Another common pitfall is not trimming whitespace around the input string. For example, 192.168.1.1 or 2001:0 DB81 may fail validation if leading or trailing spaces aren't removed first. It's important to trim the input before processing because many programming environments allow strings with extra spaces. Overcomplicating the logic, especially with regular expressions, is another issue. While regex can be powerful, writing overly complex patterns to validate IPv4 or IPv6 addresses can make the code difficult to read and prone to errors. For problems with many edge cases, regex can quickly become unwieldy, so it's often better to use straightforward parsing or modular functions for clarity and maintainability. To perform well in interviews, it's crucial to understand the differences between IPv4 and IPv6 formats. IPv4 consists of 4 decimal numbers separated by dots, each ranging from 0 to 255. IPv6, on the other hand, uses 8 groups of hexadecimal numbers separated by colons, and it allows compression with a double colon, smiley face, to represent omitted zeros. Being aware of edge cases is just as important. Test inputs like 0.0.0.0 or 255.255.255.255 for IPv4, and for IPv6, check examples like :1 or mixed-case hexadecimal like ABCD 1234. Keeping your implementation modular is another key tip. By separating the logic for IPv4 and IPv6 into distinct functions, you can simplify debugging and enhance readability. Finally, while validation is typically efficient due to fixed input lengths, avoid unnecessary computations or redundant string operations to optimize for performance. Once you understand how to validate IP addresses, you might want to explore related problems to deepen your skills. LeetCode 468, the problem we're focusing on, is directly about validating IP addresses. LeetCode 93, Restore IP addresses, takes this further by asking you to generate all possible valid IPv4 addresses from a given string. Another related problem is LeetCode 1108, Defanging an IP address, which is more about simple string manipulation. Finally, there's LeetCode 819, Most Common Word, which emphasizes string parsing and handling edge cases, a skill set that overlaps significantly with IP address validation. These problems provide an excellent opportunity to practice similar concepts in different contexts. When approaching IP address validation, there are several strategies you can consider. One is string parsing using the split function, which divides the input based on dots or colons. This approach is simple and effective but requires additional checks, such as verifying segment lengths and numeric ranges. Another option is to use regular expressions. Regex allows you to define compact patterns for IPv4 or IPv6 formats, but it comes with trade-offs. Patterns can become hard to debug and may fail to account for edge cases like empty segments, smiley face. A third approach is character-by-character validation, where you manually iterate through the string, validating individual characters and segments. While this gives you more control, it can lead to verbose and error-prone code. Each approach has its strengths and weaknesses, so choose the one that best suits the problem's requirements and your own coding style. Great job! To recap, we solved the problem by implementing a string parsing solution to validate IP addresses. This problem highlights the importance of handling edge cases and precise string manipulation. Thanks for joining, and don't forget to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!